Good day, students. Welcome to mathgotserved.com. In this clip, we're going to be going over problem number 25 of our epic must-know mathematical induction proofs. We're going to be proving the inequality 2 to the n is less than n factorial for all integers n, where n is greater than or equal to 4. Don't forget to take a look at the links in the description below to gain access to the remainder of the must-know mathematical induction proofs. You can also gain access to those proofs at our website on mathgotserved.com under pre-calc and discrete math. Alright, so we're going to prove, let's write down what we're proving. Problem 25, we're to prove that 2 to the n is less than n factorial for all integers n, where n is greater than or equal to 4. Alright, so let's commence with the proof. To get us started, we're going to rewrite this inequality statement using Sn. Okay, so let's refer to the inequality statement. Two to the n is less than n factorial as Sn, S sub n, okay? So what we're going to do in essence is we're just going to prove, we're trying to prove S sub n, which is that 2 to the n is less than n factorial for all n in the set of natural numbers and n is greater than or equal to 4. All right, this just means n is a positive integer and then n is greater than 4. All right, so let's go ahead and take a look at the procedure that we're going to use for this problem. So we're just going to be using the same standard procedure for proving math induction, which is you have a base case, which is the foundation, inductive hypothesis, and inductive step. If you can show that the base case holds, and then the inductive step holds, assuming that the inductive hypothesis is true, then it will hold for all the conditions of your specified domain. All right. So something to keep in mind in this particular example is that we're starting with 4. N is greater than or equal to 4. So we're going to first of all show that S4 is true. A lot of math induction proofs starts at S1. So you need to be careful to pay close attention to the domain restrictions when proving by mathematical induction, okay? So we're going to show S4 is true first for the base case. Inductive step, assume S sub k is true. Inductive hypothesis, sorry. And then we try to prove the inductive step assuming the inductive hypothesis. If we can do that, then we know that that domino effect is going to take place for all integers in the specified domain. Alrighty? Okay, so let's do it. We're going to start with part 1, which is the base case. So what are we doing for the base case? So for the base case, our task is to show that S sub 4 is true. Okay? What does S sub 4 is true mean? If n is equal to 4, does this inequality hold? That's basically what we're trying to say. All right, so let's do it. So S sub 4 is what you get when you replace all the n's in the statement with 4. Remember, S sub n is 2 to the n less than n factorial. Okay, so S sub 4 is going to be 2 to the 4 is less than 4 factorial. We do not know if this is true, so we're going to put a question mark here. Is 2 to the 4 less than 4 factorial? So we're going to simplify both sides completely and then see if the inequality statement is true or false. So 2 to the 4 is 2 times 2 times 2 times 2, or 4 times 4, which is 16. Is 16 less than, now remember what factorial is, right? You count down all the way to 1 and you multiply the numbers in your countdown. So We're counting down from 4 all the way to 1, and we'll find a product of all those numbers in descending order. So we have 4 factorial is 4 times 3 times 2 times 1. Bam, like that. So is 16 less than this number right here? Well, let's see. Is 16 less than 4 times 3 is 12. 12 times 2 is 24. Is 16 less than 24? Yes, it's true. So our base case, our foundation holds. So let's write that down. The base case. The base case S sub 4 is true. So we are done with part 1 of the proof. Excellent. So we're now going to move on to our inductive hypothesis, which would be what we'll use as the basis for the inductive step. Okay, so part 1, check. Part 2, inductive hypothesis. We're going to make an assumption here, okay? So your inductive hypothesis is we're going to assume that S of k is true. Okay? S of k is true for some k in the set of natural numbers, and k is greater than or equal to 4. Alright, so let's go ahead and write down the formal statement. So in the inductive hypothesis, this is what we're going to do. We're going to assume that the statement S sub k, which is 2 to the k, is less than k factorial. You notice S sub k basically means that we replace all the n's with k, okay? Because we're picking some arbitrary k in the acceptable domain. All right, so for some random k in the set of all integers where n is greater than, where k is greater than or equal to 4, we're assuming that this is true. So assume that this statement is true for some integer k where let's be specific here. Yeah, well, it'll suffice. We're basically looking at positive integers for some integer k where k is greater than or equal to 4. When we put this constraint, k is greater than or equal to 4, it automatically means that k is positive. All right. So for some positive integer k greater than or equal to 4, this is sufficient. So let's assume that this statement is true. Okay. So if we can now go to the next step. All right. So we make the assumption. Now the next is the inductive step. Inductive step. So what we're doing is basically setting up a domino effect to guarantee that if one sequence of steps works, then it has a domino effect on every other step for all the integers. All right, so we don't have to do it for every single case. If we can just use this inductive hypothesis and inductive step, then we can show that it will always hold true. All right, so for inductive step, our task here is to show that S sub k is true follows that the next step, S sub k plus 1, is also true. All right. So we're going to start with S sub k plus 1 and see if we can use this inductive hypothesis to show that S sub k plus 1 is also true based on our inductive hypothesis. Alrighty. Okay, so let's start with S sub k plus 1. Start with S sub k plus 1, the next step. What is the S sub k plus 1? We just substitute k plus 1 for the ends, right? So we have 2 to the k plus 1. Now, can we show that this 2 to the k plus 1 is less than uh, k plus 1 factorial? That's the goal, okay? So let me just put a side note here. So goal is to show that 2 to the k plus 1 is less than k plus 1 factorial using, we have to use the inductive hypothesis using S of k. So that's what we're going to do. Okay? All right, so we have the left side down. We want to show that it's less than k plus 1. All right, so first thing we're going to do is apply the property of exponents. When you multiply two exponents of the same base, you add the power. So we're going to go backwards on that. All right? So we have the sum of powers. So it's basically the product of two exponents of the same base. And the exponents will be the addends of your power. So 2 to the k plus 1 is 2 to the k times 2 to the first power. Bam. All right. So the goal here is when you break it apart, we want to see, can we make any substitutions here utilizing our inductive hypothesis? Now you notice we have a 2 to the k in our inductive hypothesis. But what do we know about 2 to the k? We know that it's less than k factorial. Okay, so let's make a substitution here. So since 2 to the k is less than k factorial, that automatically follows that this statement right here, 2 to the k times 2, is going to be less than what? It's going to be less than k factorial times 2 using our inductive hypothesis. All right, since 2 to the k is less than k factorial. Okay, so check this out. If you have 2 to the k is less than k factorial from our inductive hypothesis, and you multiply both sides by 2, bam, bam, what do you have? You have a situation where 2 times 2 to the k is less than k factorial times 2, right? So that's what we're doing. Since 2 to the k is 2 to the k times 2 is less than k factorial times 2, and 2 to the k plus 1 is equal to 2 to the k times 2, then we can just make the substitution. We know for sure that 2 to the k plus 1 is less than k factorial times 2 because these two are exactly the same. Okay? All right, bam. So we have that right there. Make the substitution. Okay, so now what do we know about k factorial times 2? Okay, so just remember that this we have right here is based on the assumption that we made earlier over here. Now looking at k factorial times 2, we're going to take a look at the domain of our proof and see how we can use that to see how this compares with k plus 1 factorial. Okay, so what do we know about the domain? We know that k has to be bigger than or equal to 4. All right, so since k is greater than or equal to 4, how does 2 compare with k? If k is greater than or equal to 4, that means 4 is less than or equal to k. And we know for sure that 2 has to be less than k because 4 is greater than 2. Okay? So since 2 is less than 4 and 4 is less than or equal to k, it follows that 2 is less than k. All right? Now, how does 2 compare with k plus 1? If 2 is less than k, then for certainty 2 has to be less than k plus 1 because k is a set of integers that are greater than 4. All right? Now, let's go ahead and see what happens. What if we multiply both sides of this inequality by k factorial? All right? So if we multiply both sides by k factorial, we know that k factorial, k factorial times 2 is going to be less than k factorial times k plus 1. How do we know this? Well, k factorial by definition is always greater than 0. All right, if you multiply an inequality with the same positive number both sides, the orientation doesn't change. Okay, the magnitude doesn't change. When you multiply by negative, then that's when the inequality flips. Since k factorial is bigger than 0, when you multiply an inequality by that, the inequality does not change. All right, since k factorial is greater than 0, by definition, the factorial starts from 1. Okay? All right, so now we have this scenario right here. What we can do is make another substitution. Okay, so look at what we had earlier. We said 2 to the k plus 1 is less than k factorial plus 2. And now we have another situation. The same k factorial times 2, how does it compare to what we just created? It's less than k factorial times k plus 1. All right? So since k factorial times 2 is greater than 2 to the k plus 1, and k factorial times 2 is less than k factorial times k plus 1, if we use the transitive property of inequality, what can we say? You know what? Let me just write this here so it's easy for you to see what's going on. All right, so 2 to the k plus 1 is less than this, and this is less than that. Using the transitive property of inequality, it follows that, which follows that 2 to the k plus 1 is what? It has to be less than k factorial times k plus 1. Okay? What are we using here is the transitive property of inequality. Transitive property, I'm going to write it down here. Transitive property of inequality. Hopefully you remember that. Transitive property of inequality. What on earth is the transitive property of inequality? Let's take a look at that real quick. So the transitive property of inequality just states that if A is less than B, all right, and B is less than C, then what? Then A is less than C. It's pretty intuitive. Okay. All right. So that's what we're using here. Is the transitive property of inequality. Now we're going to use the definition of factorial to simplify the right side. All right. What is k factorial times k plus 1? K factorial times k plus 1 is like we are reassembling the factorial numbers. Okay, so k factorial times k plus 1 is simply k plus 1 factorial. All right, just like, for example, if you have 5 factorial is equal to 4 is equal to, what is 5 factorial? 5 factorial is 5 times 4 times 3 times 2 times 1. All right, but if you assemble these 4 digits together, that's 4 factorial, isn't it? So 5 factorial is the same thing as 5 times 4 factorial. All right, it holds for all n's, right? So n factorial is the same thing as n times n minus 1 factorial. If you do n plus 1 factorial, which is what we're doing right here, is the same thing as that number, n plus 1, times the number before it, factorial, n factorial. Okay? In this problem, in this proof, we're going backwards. We're assembling the numbers. Okay? So the number before k plus 1 is k. So k factorial times k plus 1 is simply k plus 1 factorial. Voila, this is exactly what we're trying to show. All right, so we've been able to show that S sub k is true, follows that S sub k plus 1 is also true. Is also true. All right, so let's go ahead and write down our conclusion. What can we conclude? So we're just going to restate what the proof asks us to do using mathematical induction. Okay, so by mathematical induction, the statement 2 to the n is less than n factorial is true for all integers n where n is greater than or equal to 4. Alrighty, and then put your nice little box of accomplishments to indicate that you've concluded the proof. Thanks so much for taking the time to watch this presentation. Please help support our channel by liking, subscribing, and sharing the contents of this presentation with your friends. Tons of support resources can be found on mathgotserved.com. Also, don't forget to take a look at the links in the description below to gain access to a wide collection of math induction proofs that we have, also accessible at mathgotserved.com. Thanks again for watching, and we'll see you in the next video. Bye-bye.